In this video, I'm going to show you the binomial theorem and how you can raise a binomial to a power using a tool called Pascal's triangle. So for a general statement of what the binomial theorem is saying, it's describing to us how we can take a binomial and raise it to a power. And then instead of having to multiply it all out by distributing over and over and over again, we're going to use another system to figure out all of the various terms that can be added together as a polynomial that is equal to that binomial raised to a power. So the number of terms you have will vary based on the size of the exponent. This is an example I'm going to work out in a little more detail later, but basically you can see that the bigger the exponent, the more terms you will have. So that's why there's a ... here to indicate that how many terms you have will vary. So in general terms, we really can't show it's always going to be 5 or always 6. The number of terms you have will be one more than the exponent. So each term has three parts. There's a p, an a, and a b. The p part we're going to look at on the next slide. This is going to be a series of numbers we will learn to generate using something called Pascal's triangle. So that will come up on the next slide, but you can see that each term has one of those p numbers attached to it. Next, you have whatever a is, a being the first term inside of the binomial. It's going to start at whatever exponent you have. So for example, this one would start with x to the fourth power. X is in the a spot. I'm starting with the exponent I have outside the binomial, so it'd be x to the fourth, and then it's going to decrease. So x to the third, x to the second, x to the first, x to the 0. So that's what this is indicating with the a's. Subtract 1 from the exponent, subtract 2 from the exponent, all the way down to 0. B is going to do the opposite. So b is the second term inside the binomial. This one is going to start at the 0 power, so b to the 0, and then it's going to count up. So add 1, add 2, add 3, add 4, all the way up until you get to b to the n power. So again, those numbers will be easier to demonstrate once we have a specific example to look at on a later slide. So the first part of each term I mentioned came from Pascal's triangle. This is Pascal's triangle, and you can see several demonstrations of it being applied to different binomials raised to different powers. I'm going to show you another row in just a moment as well, but this can be extended to whatever exponent you want. You could go down to the 37th row if you would like. So the way we create Pascal's triangle, you start with ones down the outside of this triangular shape. So I know if I want to create the fifth row that it's going to be another 1 and another 1 on the outside. And then you don't need to memorize all these numbers. There's actually a process to this. Every time you see a pair of numbers, you're going to add those two numbers up and put the sum in between them in the next row. So 1 plus 1 was 2. If you look at this next row, I have a pair of numbers here. 1 plus 2 would add up to equal 3. I could do the same thing for this other 3. Going to the right side of the 2, I have 2 plus 1. That's a pair of numbers. Adding them up in between in the next row is a 3. If I go to the next row, 1 plus 3 is 4. If I look in between the 3's, 3 plus 3 is 6. So the way I would connect my next row, I have 1 plus 4. That means I know that the next number down here is a 5. Then I have a 4 plus 6. If I add up those two numbers, the next digit would be 10. And then repeating a 10 again, because I have 6 plus 4 again. And then I have a 4 plus 1 again, so this is a 5. So you can see that every time you go down another row, you're going to have one more number than you did in the row before it. So when you get to the power expansions, this would have been for the a plus b to the fifth power. Now I know that my coefficients, instead of being 1, 4, 6, 4, 1, like you can see here, 1, 4, 6, 4, 1. Now I know that my terms would be 1, 5, 10, 10, 5, and 1. So those are the coefficients, and then you would use the other pattern described on the last slide to start with a to the fifth power, a to the fourth power, a to the third power, a to the second power, a to the first power, a to the 0 power, and the b would count up. So it would be b to the 0, b to the first, b to the second, b to the third, b to the fourth, b to the fifth. You could, like I said, take this down more rows if you want. So then the next row you would still have ones down the outside all the way. Add the numbers up. So the next number would have been a 6, a 15, 20, a 15, 6 again, and then ending on the 1. Now some things are easier to show on an example than to describe in words. So let's go back to the example I mentioned briefly on the earlier slide. Let's apply this process to x plus 2 to the fourth power. Well, the first thing we'll want to do is to identify the coefficients that come from Pascal's triangle. So I would look back. This row is already filled in for us, so I don't need to generate this on my own. I know that for the a plus b to the fourth power, my coefficients are 1, 4, 6, 4, 1. So basically, we want to use these 5 numbers here, and we're going to write them out with lots of space, because remember, I also have to apply what's happening to the a to a power and the b to a power for every term. So these are the coefficients for every term. So my first step, I have 1, 4, 6, 4, and 1. And each of these is going to create a different term in my polynomial. So now that we've dealt with the p-values, now let's go back to the next bullet. So now we're going to start with whatever a is, so whatever is the first term in the binomial. We're going to start with the n power, and we're going to decrease until we hit 0 for each term. On this example, my a value is x, and the exponent is 4. So I'm going to have x to the 4th power, x to the 3rd power, x to the 2nd power, x to the 1st power, and x to the 0 power. So we're just counting down, starting from the exponent for the first number. For the last piece of our binomial theorem, we're going to start with what b is, which according to the formula here is the second term in the binomial. This one's going to start from the 0 power, and it's going to increase to n, where n is the exponent. So the second term in my binomial is a 2. That means I'm going to start with 2 to the 0 power, and then 2 to the 1st power, 2 to the 2nd power, 2 to the 3rd power, and 2 to the 4th power. Once you get to this step, there will probably be some computing you have to do. Since I have some numbers that I can raise to a power, like 2 to the 0 power, 2 to the 1st power, 2 to the 2nd power, we need to compute those and then multiply any of the numbers together in each term. So the first one, and remember anything to the 0 power is equal to 1. So I can think of this as 1 times x to the 4th times 1, which is just x to the 4th. So now we're just going to be simplifying each of the individual terms we wrote. Then I have 2 to the 1st power, which is 2, times x to the 3rd times 4. Well, the 2 and the 4 can be multiplied together to make this 8 x to the 3rd. Next term, I have 2 squared, which is 4, times 6, which is 24, x squared. Next term, I have 2 to the 3rd power, which is 8, times 4, which is 32. And that's x to the 1st power, so we can just write x. We don't need the exponent on it. For the last term, I have 1 times x to the 0, which is also 1, times 2 to the 4th, which is 16. So that is my expanded binomial for x plus 2 to the 4th power. We found that instead of having to distribute out x plus 2 times x plus 2 times x plus 2 times x plus 2. So in most cases, you will find that this is much faster than having to do all the distributing, especially based on the size of the exponent. Here is a tougher example because my a value is 2x and my b value is 3y. Although I do have a smaller exponent here, we're just going to do the 3rd power for this binomial. So the first thing I need is the coefficients from Pascal's triangle. Again, I do have these coefficients already listed on what I showed you in the notes. If you needed to go down farther, you might have to create more rows. But for the 3rd power, I just need the numbers 1, 3, 3, 1. Okay, now this time our a value is 2x. So be careful and use parentheses when you write this part. This is going to be 2x to the 3rd power, and then 2x to the 2nd power, 2x to the 1st power, and 2x to the 0 power. Same thing for my b value. It has both a number and a variable. So I'm going to start with 3y to the 0. This one counts up. And then 3y to the 1st. 3y to the 2nd. And 3y to the 3rd. Since the exponents are going to be more complicated to compute, you may want to simplify this in 2 different steps instead of trying to do it all at once. So in this case, I'm going to have 1 times 2x to the 3rd power. Remember, you're having to apply the 3rd power to both the coefficient and the variable. So 2 cubed is 8. And then we also get the x cubed. And then 3y to the 0 power, anything to the 0 power is 1. Next term, I'm going to have 3 times This piece, I have 2x squared. Well, the 2 squared will give me 4x squared. And then 3y to the first power is 3y. For the next term, I have my 3 out front. 2x to the first power is just 2x. And then I have 3y squared, so squaring both the number and the variable gives me 9y squared. And for my last term, I have 1. Anything to the 0 power is 1 as well. And then 3 to the third power is 27. And the y to the third power is y cubed. And now I still need to multiply the various parts of each term. So I have 1 times 8x cubed times 1. That will be the 8x cubed. In the next term, I have 3 times 4, which is 12, times 3 again is going to be 36. And then the x squared and the y, you're not going to be changing those exponents or anything. They don't combine in any way. So x squared y. For my next term, I have 3 times 2, which is 6, times 9 is 54. And then again, the variables will stay the same, so xy squared. And for my last term, I have 1 times 27 y cubed. So that's our expansion of 2x plus 3y to the third power. For one last example, let's look at what it would look like if you were just finding one specific term in the expansion rather than the entire polynomial. First, we're going to need to make the Pascal's triangle a little bit bigger because I did not show all the way down to the binomial to the 6th power coefficients. So we start off with 1's down the outside. Remember the polynomial rows, this is actually the 0 power, 1st power, 2nd power, 3rd power. So this is the 4th power row, then the 5th power row, and then the 6th power row. I take every pair of numbers I get and I put the sum in between in the next row. So then I have 1 plus 2 is 3. So on this other side, it's a 3 as well. For the next row, I have 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4 again. Next, I have 1 plus 4 is 5. 6 plus 4 is 10. 6 plus 4 is 10 again. 4 plus 1 is 5. And for the last row I have a 6, 15, 20, 15, and 6. But we're not going to do the entire polynomial. We're actually just interested in the x to the 4th power term. Now remember, there's a pattern for what's going to happen to the a in our binomial. So since I'm using this bottom row, I know that it's going to start as x to the 6th power, x to the 5th power, x to the 4th power. So since I'm asking you for the x to the 4th term, we don't need to write out everything. We can just start with this one individual term by saying, well, it's going to use the coefficient 15. It's going to end up being x to the 4th power as indicated for the a term. And then the other part of the trinomial, the last piece, is going to be my b value, which is -2. Remember, this one counts up. So instead of -2 to the 0, -2 to the first, -2 to the second. So it's a lot easier to find an individual term when we don't need the whole polynomial. Now I just need to compute these 3 pieces being multiplied together. So I have 15 times x to the 4th. Remember, this is a -2 in parentheses squared, so that's 4. So I can just do 4 times 15, which is going to be 60 x to the 4th power. And that's it. That's the x to the 4th term from the entire expansion of x minus 2 to the 6th power. That's it for the notes, and I hope that will be helpful on how to expand binomials using Pascal's triangle.